Hello friends, this is Priyanka. Today we are going to solve a problem on Nyquist plot. In this video, we are going to determine the range of k for the stability of the system. So let us first understand what is the given open loop transfer function. G of s h of s is equal to k in bracket 1 plus 0.4s into s plus 1 divided by 1 plus 8s s minus 1. So for this open loop transfer function, we have to find out the range of k for the stability of the system. We have to first find out how many number of poles are there for this given open loop transfer function. So to find out the number of open loop poles, we have to take denominator is equal to 0. So when we take denominator is equal to 0, then this first bracket is also equal to 0. So I will say that 1 plus 8s is equal to 0. Therefore s is equal to minus 1 by 8. So if we calculate this, that is 1 divided by 8, that is equal to 0.125. So I will say that minus 0.125. Then this second term is also equal to 0. S minus 1 is equal to 0. Therefore s is equal to plus 1. Now if we observe, this first pole is having negative sign. So here this is the real axis, this is the imaginary axis, and here is origin. On the right hand side, so I will say that this is the right hand side and this is the left hand side. So on the right hand side, we have to take this s is equal to plus 1. So here is the pole, open loop pole, and this s is equal to minus 0.125, that is on the left hand side. So we know that whenever there is any open loop pole is on the right hand side of the s plane, then we can say that the system is unstable. So here we will mention this is important thing, that is we have to take the number of poles on right hand side of s plane is equal to 1. So we will use here the notation as a p is equal to 1. So this is important information, and this information we will use to determine the stability of the system, or we can say that to determine the range of k. So this is the important point. Now we will move for the Nyquist plot. So if we observe here, there is no any pole at the origin, because there are only two poles. One pole is on the left hand side and other pole is on the right hand side. So whenever there is the pole is at origin, then we have to take the 4 sections. But here no pole is at origin, so we will consider here the 3 sections for the Nyquist plot. And now we will understand one by one section. Now here I will highlight the section 1. This section is known as section C1. Now how we will understand this section? Now here is the origin, and that is we will say 0, and it moves to the imaginary axis in the upward direction. So for this imaginary axis, all the numbers is having plus sign, and final number is plus infinity for this side. So we can say that for this C1, or for the mapping of this section C1, we have to put s is equal to plus j omega, and whenever there is s is equal to plus j omega, then this plot is known as polar plot. This plot is known as polar plot. Now if we observe, this section starts from 0 and end towards plus infinity. So we can say that omega vary from 0 to plus infinity. So this is important point, omega vary from 0 to plus infinity. Now we will move for the second section. So I will highlight here the section 2. So how we will define this section C2? Here we have to put s is equal to r e raised to j theta, where r tends to infinity. And e raised to j theta indicates us the phase angle, where in this theta will vary from plus pi by 2 to minus pi by 2. Now how we can say that? Because if we observe, this section C2 starts from this point, and at this point here angle is plus pi by 2 or plus 90 degree, and here angle is minus pi by 2 or minus 90 degree. So this section C2 starts at this point and ends at this point. So theta will vary from this plus pi by 2 up to minus pi by 2. So this is about the section C2. Now we will move for the third section. So I will highlight this. Here this is the section C3. Now how we will define the section C3? So if we observe, this is on the lower part of the imaginary axis, and all the signs for this imaginary axis are negative. So we have to put here S is equal to minus j omega, and this plot is known as inverse polar plot. Now how we can say that the variation of omega? If we observe this section here is the minus infinity sign. So this section C3 starts from this minus infinity and end towards the 0. So we will say that omega vary from minus infinity to 0. We can also say that this polar plot and this inverse polar plot are mirror image to each other, and these are in the opposite direction to each other. As we have to determine the range of K for stability of the system, we will draw polar plot and inverse polar plot. That is section C1 and section C3. No need to draw section C2. So for this section C1, we will first put this given transfer function S is equal to j omega. So first step is to put S is equal to plus j omega. Then g of j omega, h j omega is equal to k 1 plus 0.4 j omega 1 plus j omega divided by 1 plus 8 j omega and j omega minus 1. Now we have to find out what is the magnitude and phase angle. So how we can find out the magnitude? So we know that magnitude, that is nothing but modulus of g j omega h j omega. So what is the rule for this magnitude? So we know that whatever is the j omega term or s term in this given transfer function, we have to take the square root and square simultaneously. So we will follow this rule, that is k we will write as it is. Now here this is the term in the form of j omega. So how I can write here? That is, I will take first square root and now I will square these terms. So what is the square of 1? That is 1. And what is the square for this 0.4 j omega? So 0.4 square, that is 0.16. Now j square, so we know that j is equal to under root of 1 minus 1. So j square is equal to minus 1. But here in magnitude we have taken this modulus. So whenever we take this modulus of j square, all the minus sign will become plus. So we have to take here j square as a plus 1. So this j square is a plus 1 and remaining term, that is omega square, we will write as it is. Now in the same way for the second term also we have to take square root. Now square of 1 is 1 and plus j square omega square, but this modulus of j square is plus 1, so I will take here omega square. Now we will move for the denominator. We have to take square root for this term, then 1 plus square of 8, that is 64, j square omega square, but j square is plus 1, so I will write here omega. For this term also we have to take the square root and square simultaneously, so I will take here square root of j square omega square, that is omega square. Now here minus 1 is there, but because of modulus minus 1 will become plus, and here is omega square plus 1. Now again if we observe here under root of 1 plus omega square and here is also under root of 1 plus omega square. These two terms is getting cancelled. So I will again write the next step, that is k under root of 1 plus 0.16 omega square divided by under root of 1 plus 64 omega square. So here this is the final magnitude. So we can use the different values of omega and we can find out the magnitude. Now we will move for the phase angle. So how to calculate the phase angle? That is angle of Gj omega Hj omega is equal to. Now if we observe this transfer function, then for this transfer function we have to take tan inverse of imaginary part divided by real part. So imaginary part is nothing but which contains this j omega term. Then whenever this j omega term is in the numerator, then we will use the plus tan inverse, and whenever this term is in the denominator, then we will use the minus tan inverse. So how we can use this? So I will refer this 1 plus 0.4 j omega, that is this term is in the numerator, so plus tan inverse of imaginary part by real part. So imaginary part is 0.4 omega, real part is 1, so no need to write. Then again for the second term, this term is also in the numerator, so I will use plus tan inverse of imaginary part by real part, that is tan inverse of omega by 1, so we will write only omega. Now we will move for this term. So this term is in the denominator, so I will use minus tan inverse of imaginary part, that is 8 omega by 1. So I will write here 8 omega. Then we will move for the next. So here is also minus tan inverse of imaginary part by real part. So real part is having minus sign. So I will use here minus tan inverse of omega by minus 1. Now we will simplify this term. So how to simplify? So for that I will write here plus tan inverse of 0.4 omega plus tan inverse of omega minus tan inverse of 8 omega minus, now here how we can simplify this? So we have to remove this minus 1. So how to remove? So I will write here pi minus tan inverse of omega. So for this both the meanings having same, that is tan inverse of omega by minus 1, that is equal to pi minus tan inverse of omega. So I will again simplify this. I will use this, I will multiply this minus sign inside the bracket. Tan inverse of 0.4 omega plus tan inverse of omega minus tan inverse of 8 omega minus pi plus tan inverse of omega. So this is the final formula that we have to use to calculate the phase angle. For the mapping of section C1, we know that omega varies from 0 to plus infinity. So to draw the exact polar plot related to section C1, we will take the different values in between 0 and infinity. So if I take the first value of omega, that is 0, then what is the value of magnitude? So magnitude is k under root of 1 plus 0.16 multiplied by 0. So this term will become 0. So k under root of 1 divided by under root of 1. So we can say that magnitude is only k. So we will write here magnitude k. Now what about the phase angle phi? So if we put here omega is equal to 0, then tan inverse of 0 is 0. Then here is also 0, 0 minus pi, and here tan inverse of 0, 0. So the remaining value is only minus pi, that is minus 180 degree. So we will write here phase angle phi is equal to minus 180 degree. Now in the same way we have to take the different values. So next value we will take, we can choose any random value. So I will choose here 0.3. So when we put omega is equal to 0.3 and calculate, we will get magnitude 0.387 k and phase angle minus 207.2. Now when we put here 0.5, then 0.247 k and angle minus 191.5 degree. Then omega, for omega is equal to 1, it is 0.133 k angle minus 151.07. For omega 5, 0.055K and angle minus 47. For 10 it is 0.0515K and angle minus 24.7. For 100 it is magnitude is 0.05K and angle minus 2.5. So if we observe, this angle is very nearer to 0. So after that, if I use very large value, that is suppose we will take omega is equal to 10,000, then what is the magnitude? So magnitude will remain same, that is 0.05K and angle will become nearer to the 0 or 0 degree. So we can say that instead of writing this 10,000 or 1 lakh, we will write here as a infinity, because after that this magnitude will remain same, that is 0.05K and angle, phase angle phi, that is 0. So in this way this table is getting completed. And for the mapping of section C1, where is the start point? So start point when omega is 0. So this is the start that we have to take, and here is the end point, because omega varies from 0 to infinity. So for this infinity, this is the end point. That means for magnitude, start magnitude we will take K and end is 0.05K. Start angle we will take minus 180 degree and end is 0. So this is important, that this is the start and this is the end for this section C1. Now we will find out what is the point of intersection of Nyquist plot with real axis. So for that we have to show imaginary part is equal to 0. So in this open loop transfer function we will put S is equal to j omega. Now from this denominator we have to remove all the imaginary part. So for that we have to multiply this with complex conjugate number. So what is the complex conjugate for this 1 plus 8j omega? It is 1 minus 8j omega. And here for this j omega minus 1, it is minus 1 minus j omega. So remember complex conjugate for this imaginary part. So here is the plus sign for this imaginary part. So we have to take the minus sign for both of these brackets. So from the numerator and denominator we have to take this complex conjugate number. So total effect is getting cancelled. So how to write this? So I will write here K 1 plus 0.4 j omega plus 1, and in the denominator I will write 1 plus 8j omega. So I will multiply here with 1 minus 8j omega, and here j omega minus 1. So I will multiply here minus j omega minus 1. So these two are the new terms. So I will take here in the numerator also 1 minus 8j omega and minus j omega minus 1. Now if we observe this denominator here, this is a plus b, a minus b. So what is the meaning of or how we can write this in other way, that is a plus b, a minus b, that is equal to a square minus b square. So again I will write that. Now at the same time we can multiply these brackets. So I will multiply these two brackets and these two brackets in this step. So which is equal to K. Now if I multiply these two brackets, then 1 multiplied by j omega, that is j omega plus 1 plus 0.4 j square omega square. So here we know that j square is equal to minus 1. So I will write here minus 0.4 omega square, then 0.4 multiplied by 1, that is plus 0.4 j omega. So this one bracket is getting completed. Now we will multiply these two brackets. So here 1 into minus j omega, that is minus j omega, 1 multiplied by minus 1, that is minus 1, minus 8 j omega minus j omega. So this minus will become plus. So here plus 8 j square omega square. So j square is nothing but minus 1. So I will write here minus 8 omega square. And here minus 8 j omega minus 1. That is minus will become plus 8 j omega. So this bracket is also getting calculated. Now we will move to the denominator. So here this is a square minus b square, that is a is nothing but this 1 minus b square. So b square is 8j omega square, that is 64j square omega square. So j square is minus 1, so this minus minus will become plus, that is 64 omega square. Now in the same way here is also a square minus b square. So if we take here this minus 1 term, that is a, so minus 1 square minus b square, so b square is j omega square. So how we can write this? Minus 1 square, that is 1 minus j square omega square, so j square is minus 1, so it will become plus omega square. So if we observe in this denominator, all the terms are having this real number, so no any imaginary part is there. So if we will concentrate on this numerator, so in numerator there are the imaginary parts, so we have to separate this real part and imaginary part. So how to separate? So again we have to take first we will simplify these two brackets and then we will multiply these two brackets with each other. So if we observe here minus 0.4 omega square, so I will write here minus 0.4 omega square, then plus 0.4 j omega plus 1 j omega. So here j omega plus 0.4 j omega. So we can say that here coefficient is 1. So 1.4 plus 1.4 j omega, and here is plus 1. So this is only simplification. Then here minus j omega plus 8 j omega. So first I will write here minus 8 omega square, then 8 j omega minus 1 j omega, that is 7 j omega, and minus 1. So these are the two brackets and here k is already there. Again we will simplify this, that is we will multiply these two brackets with each other. So if we observe here is plus 1, so we will write here, and we will multiply these two brackets with each other and we will separate the imaginary part and real part. Now we will multiply with these two brackets. So minus 0.4 omega square multiplied by minus 8 omega square. So here minus minus will become plus 3.2 omega raised to 4. Then minus 0.4 omega square multiplied by 7j omega. So here minus 2.8 j omega cube. Then we will multiply with this third number, that is minus minus will become plus, and here 0.4 omega square. Then we will move for the next number. So 1.4 j omega multiplied by minus 8 omega square. So here minus 11.2 j omega cube. Then 1.4 j omega multiplied by 7 j omega. So here j omega, that is j square omega square. So for this j square we will use minus and 9.8 omega square. Then again this 1.4 j omega multiplied by minus 1. So here minus 1.4 j omega. So for this one also we will multiply this whole bracket. So here minus 8 omega square plus 7 j omega minus 1, because it is getting multiplied by 1. So we have to write as it is. Bracket complete is equal to 0. Now from this we will take separate what is the imaginary part. So imaginary part means what? Which contains the term j omega. So if we observe minus 2.8 j omega cube. So this is one number, and here is also minus 11.2 j omega cube. So these two numbers are imaginary. Now in the same way here minus 1.4 j omega and plus 7 j omega. So we can combine this because j omega cube, j omega cube. So here is coefficient minus 2.8 and here is minus 11.2. So minus 2.8 minus 11.2. Suppose we take minus sign as a common, then here we will get 14 j omega cube. So we will write here as a minus sign. Then here coefficient is 7 and minus 1.4 for this j omega. So 7 minus 1.4, that is equal to 5.6 j omega. So here we will use plus sign and we will equate it to 0. Now if we observe from this equation, we can take j omega term as a common term. So j omega in the bracket minus 14 omega square plus 5.6 is equal to 0. So how to write the solution? So we can write here j omega is equal to 0 and we will take here omega square is equal to. So I will transfer here this 5.6 to the right hand side. So minus 5.6 divided by this minus 14. So omega square is equal to 0.4. So we will get here two solutions. J omega is equal to 0 and this bracket is equal to 0. So when this bracket is equal to 0, then value of omega square is equal to 0.4. So now we will take the square root, that is square root on both sides. So omega is equal to plus minus 0.632. We get the two values of omega. Omega is equal to 0 and 0.63. Now how to find out the point of intersection with real axis? So for that we have to put this value of omega to calculate the magnitude. So we will calculate the magnitude, that is the modulus of gj omega hj omega. So formula that is already there, that is k under root of 1 plus 0.16 omega square divided by under root of 1 plus 64 omega square. So instead of omega square we will put here omega square is equal to 0.4. So when we calculate this we will get 0.2k. Now we will move to draw the polar plot. So for that we have to first draw here real axis and imaginary axis, and now phase angle 5 varies from this minus 180 degree up to 0. So these are the phase angles that we will draw. So I have drawn all these phase angles with this red marker. Now we have to plot the magnitude. So this is the start point and here is the end, because omega vary from 0 to infinity for section C1. So this is the start point. So we have to start from omega is equal to 0. So omega is equal to, when omega is equal to 0, magnitude is equal to k. So how to plot this magnitude? So we will refer here one particular scale for value of k. That is, suppose we will take k is equal to 10 centimeter. Then all these magnitudes will vary accordingly. That is, for this 0.3 it will become 0.387 multiplied by 10. That is 3.8 centimeter. So I will take here k is equal to 10 centimeter. So this is the approximate scale, that but we have to write here the scale k. So suppose this point is, we will select, and this total distance, suppose there is k, then I will write here this is the k distance. So this is the magnitude, and what is the angle? Here angle is minus 180 degree. So here this is the start point. Now we will move for the next point. So here for omega 0.3, magnitude is 0.387 and angle is minus 207 degree. So for this minus 207 degree here, this is the angle, and for this we have to select here the particular magnitude. So what is the magnitude here? That is 0.387 k. So here k we have selected 10 centimeter. So 10 multiplied by 0.387, that is 3.8 centimeter. So approximately 4 centimeter we will select here point. Then we will move for the next. So for 0.5 again angle is minus 191.5. So here is the angle minus 191 and magnitude is 0.247. So 0.247 k. So if we multiply with 10, then we will get 2.4 centimeters. So approximately 2.5 centimeters we will select here one point. So we have to take all these magnitudes and angles. So here the next is minus 151. So here is minus 151, magnitude is 0.133. So 1.3 centimeters. So we will select here one particular point. So all these points are getting selected, and at this minus 2.5 degree, here 0.05 k. So this is the point with 0.05. So approximately, suppose k is 10 centimeter, then we have to take 0.5 centimeter, that is half centimeter distance, and here is also 0 degree, same distance is there, that is 0.5 centimeter. So this will depend on what value of k that we will take. So if we take the value of k 20 centimeter, then we have to multiply here with 20, and accordingly we have to refer here the scale. Now we will join. So starting point is K minus 180 degree. So here is the point. So we will join here the next point. Then now here remaining points are here. So we will refer the point of intersection. So point of intersection is 0.2K. So 0.2 multiplied by 10, that is 2 centimeters. So from here we will take the 2 centimeter distance, and this point will be point of intersection on real axis. So we have to move here, it's smooth curve, and then we will join all these points. So we will show arrow also. So here is the start point and here is the end point. So we will show arrow in this direction. So I will refer here magnitude. So for minus 180 degree magnitude is K, and for this infinity angle, for omega is equal to infinity, angle is 0 degree and magnitude is 0.05 K. We will refer here, this is the point of intersection and that is equal to 0.2 K. So I will write here as a 0.2 K. So this is the point of intersection. Now we will draw inverse polar plot. So inverse polar plot is the mirror image for this polar plot. So if we observe omega is equal to infinity, this is the end point, and at magnitude 0.05 K and angle 0 degree. So for this polar plot, this is the end point, and inverse polar plot we have to start from this point and we have to draw the mirror image for this. Here is the one. So we will show arrow also. So arrow from this end point towards the start point of the polar plot. So arrow we have to show in opposite direction. So this is the Nyquist plot. Now we have to determine the range of K for the stability of the system. To determine the range of K for stability of the system, we will use here the formula N is equal to P minus Z, where the value of P that is known, that we have already calculated the number of open loop poles on the right hand side of the plane, that is P is equal to 1, and that we already know. So what is this value of N? That is the point minus 1, 0. For this point, number of encirclements, that is the value of N. And what is this Z? That is the number of closed loop poles on the right hand side of the plane. So if we calculate this value of Z, that is number of closed loop poles, is equal to 0 on the right hand side plane, then only we can say that the system is stable. So for that we have to first take this value of N, that is the number of encirclements, and for that we will find out the range of K. P is equal to 1, that we already know from this transfer function. Now we will find out for which value of N, that is the value of Z will become 0. So for the case first, I will take the range of K is in between 0 and 1. That is K is greater than 0 but it is less than 1. So we know that in this structure, if I use this, here is the point 0 is there and here is the point 1. So K is in between 0 and 1. Anywhere in between 0 and 1. So how to find out the number of encirclements? So for that we have to show this minus 1, 0 point. Number of encirclements for this minus 1, 0 point we have to find out. So it is not enclosed by any circle because here the range of K is less than this point, minus 1, 0. So K may be here, here or somewhere here in between 0 and 1. So number of encirclements is equal to 0 here. Now we will put this value of N and value of P in this formula. So 0 is equal to 1 minus Z. So what is the value of Z? Z is equal to 1. So when Z is equal to 1, that means the number of closed loop poles on the right hand side is equal to 1. And that's why system is unstable. Now we will move for the next range. So for the next case we will take K is in between 1 and 5. That means if I select here the number 1 and if I select here the number 5, then k, range of k is in between 1 and 5. So I will write here this point that is on negative side. So I will write here this is the point of minus 1 comma 0. So in these two, this is the range for k. Then we have to decide whether the system is stable or not. So from this we can say that k is greater than 1. Then we will find out the location of point of intersection. So this is the point of intersection, that is 0.2k. So for this 0.2k, how to decide? So maximum range of k is 5. So suppose I will take here 5, then k 0.2k is less than 1. So we can say that k is less than 5 and therefore 0.2k, that is, suppose I will take k is equal to 5, then 0.2 multiplied by 5, that is equal to 1. So this 0.2k is less than 1. So we can say that in this diagram, here is the unit 1. So point of intersection somewhere here, but it is less than 1. So if we select this range, 1 is less than k is less than 5, then what is the number of encirclements, that is the value of n. So if we observe this diagram, here minus 1 comma 0 point is getting encircled or enclosed by one circle. Now here it is important to note that the direction for this circle. So this direction is in the clockwise direction. So for this clockwise direction we have to use the negative sign. So number of encircles, that is number of circles enclosed for this point, that is 1. But the direction is clockwise, so I will use the negative side, that is n is equal to minus 1. So we know that p is equal to 1, so how we will calculate the value of n, that is value of z. So I will put the value, that is minus 1 is equal to p, that is 1 minus z. So again we will solve this. So minus z is equal to minus 1 minus 2, that is minus 2, and therefore z is equal to 2. So from this we can say that the number of closed loop poles on the right hand side is equal to 2. So for this range also system is unstable. Now we will select the third range as phi is less than k is less than infinity. So here if we observe, k is in between phi and infinity. So I will say that k is greater than phi. So if I select, this is the random number and here is infinity. So k is in between phi and infinity. Now we will find out where is the exact location for this 0.2k. So suppose we will take k is equal to 5, then this point of intersection is at point 1, and suppose it is more than 5, then 0.2k is greater than 1. That means this point of intersection is here and minus 1 comma 0 location of this point is for this circle, because point of intersection is greater than 1, that is this point of intersection is greater than this point, and that's why here is the location of minus 1 comma 0. So now for this point, how many encirclements are there? So it is enclosed by one circle only, and it is in the, here it is in the anti-clockwise direction. So for anti-clockwise direction we will use the positive sign. So n is equal to plus 1. So if I put here the value, that is plus 1 is equal to 1 minus z. So here z is equal to 1 minus 1, that is equal to 0. So for this number of closed loop poles on the right hand side plane is equal to 0. So we can say that for this condition system is stable.